Okay, till now we have seen about temporal logic, and we have particularly discussed one kind of temporal logic which is called CTL, computational tree logic. Till now we have seen what is the syntax of CTL and how to define the semantics. So, while defining the semantics, we need a model, and the meaning of those CTL's formula will define over a model which is basically known as your Kripke structure. Now, today we are going to see some equivalence between CTL formulas, because in logic we have equivalent formulas, in CTL also we are having some equivalent formulas. Just as a recap, you just see that in propositional logic we are having equivalent formulas, and we say that this P implies Q is equivalent to not of P or Q. So, what does it means? It says that for same assignment of truth values for P and Q, both this formula will give me the same truth values. If one will give me truth value true, then second one will also give me truth value true. If one will give me truth value false, then second one will also give me truth value false. So, it should be true for all possible assignment for P and Q. Now, here since we are talking about only two variables, that means we can have the proportional variable P and Q. They are having four different combination, maybe both are yours 0 0, or I can say that true true, or rather I should say that instead of 0 I will say that this is false, and 0 I will say that this is false, maybe it is false and true, true and false, and true and true. These are the four possible combination we have. Now, if you see these things, then for all possible combination, both the formula will give us the same truth values. In this case, we will say these are the equivalent formula in your propositional logic. So, similar notion of equivalent formula comes in our predicate logic also. In predicate logic, we are having this particular quantifiers for all x and there exists x. So, one common or basic notion of equivalent formula here we are going to get not of for all x p x is equivalent to there exists some x for which not of p x is true. Okay, so, basically p x is a predicate, it says that for all x p x is true, and negation says that we do not get any x for which p x is true. So, that means we may have we should get some x for which not of p x is true. So, this is the notion of your equivalent formulas in our predicate logic. So, like that now we have to see one will say the two formulas in CTLs are equivalent. So, what is the notion of equivalent formulas in CTL? So, you can see that two CTL formulas phi and psi. So, we are going to consider two formulas phi and psi. So, the truth values of these two formulas phi and psi will be defined with respect to models. So, we are going to say that these two CTL formulas phi and psi are said to be semantically equivalent if any state in any model. Now, this is important, any state in any model which satisfies one of them also satisfies the other. So, that means, if we are going to say that two CTL formulas are equivalent, they must have the same truth values in all state of any model. Okay. So, if we are going to consider any state, if phi is true, then psi must be true in that particular state of any model. So, if you to look for any models, then both must be true in any state or both must be for any state. Then we are going to say that these two formulas are equivalent. Now, we know the syntax of our CTL formulas, we know the meaning or semantics of CTL formula. Now, we will see what are the equivalent formula that we have in our CTL. So, in temporal logic, basically you see that we are having some temporal operators and some path quantifiers. So, with respect to these are your CTL. So, in CTL we are having A, which is called universal quantifier on paths, that means we are going to reason about all paths. E, existential quantifier on paths, that means we are going to look for any paths. These are the two path quantifiers. Similarly, we are having two temporal operator, one is G and second one is F. What G says that this is the universal quantifier of states along a path. So, basically we said that G globally it is true in all states in a path, and F we said that there we are going to get states in future where some formula or some CTL formulas are true. So, in that case we can say that f can be treated as our existential quantifier of state along a path, and g is the universal quantifier of states along a path. Now, you just see that here we are having two quantifier a and e, which is basically across path, and f and g, which are basically states along a path. So, these two things can be, again you can see that we are having that for all quantifier in predicate logic, and there exists quantifier in our predicate logic, and we know that they are having some relationship. Okay, with negation we are going to get the other. So, similar notion will be available with our this temporal path quantifier as well as the state quantifier A, E and F, G. So, for that we are going to get some equivalent formulas. We are going to see those particular equivalent formula. First equivalent formula that is coming over here is like that: not of A f phi is equivalent to there exists a plot globally not phi. Just see what it means. Not of A f phi, we know that A f phi in all part in future phi true. So, if not of these things means this particular statement is false. So, in all part in future phi is true is basically false, because we are having this particular negation symbol in front of this particular CTL formula. Now, second formula it says that E g not of phi. There is a part where globally phi is not true. So, we are going to get one part where globally phi is not true. So, now see that we are saying that these two are equivalent. How we are going to get the equivalent? With the help of small example, I am going to say that. It says that in all part in future phi is true is false. So, basically just see that we are going to define the semantics over a model. So, we will think some model something like that. Okay, so, this is a simple model. Now, we have to see that in all part in future phi holds. So, that means we should get some state in future where phi is true, and we are saying that this is not true. That what means in all paths we are not going to any future state where phi is true. At least it is not true at least in one of the path. So, basically if you say that if I am having phi is true over here, phi is true over here, phi is true over here, then in all these three paths you are going to say that A f phi is true. But in this particular path we are not going to get any state where phi is true. So, in this particular case what I am saying that A f phi is not true in this particular state, say S, where from we have started. Now, this is equivalent, we are saying that there exists a path when globally not of phi holds. So, I say that this is your not of phi holds. Basically, you said that since not of phi holds here, maybe A f phi may not be true or A f phi may not be true in this part, but what will happen in these two other two states? If phi holds over here, then f phi holds in this particular path. So, not of phi must be true over here. So, similarly, in S 0 also not of phi must be true. So, what it says that basically we are going to get one particular path where globally not of phi is true. So, since in this particular state diagram in state S, I said that these models there exists a path globally not of phi holds. Similarly, you will find that in this particular state S not of A f phi holds. Basically, we are getting one part where in future phi is not true. So, not of A f phi is true in this particular state. So, like that in this particular state these two formulas are equivalent, both are true. So, like that we will say now, if you are going to make up any model, if you will find that E g not of phi is true in a particular state, always you are going to find that not of A f phi is true. So, that is why you are going to say that these two are equivalent. You just see that path quantifier A, which is a universal quantifier, it becomes the existential quantifier across path, and the existential quantifier among states in a path becomes the universal quantifier along that particular path. So, they are dual of each other. So, in this case I am going to say that these two formulas are equivalent. So, this is the first equivalent formula that we are discussing. Now, see what are the other equivalent formula we are having. So, this is another equivalent formula we are having. There exists a path in future phi holds, and negation of this one is true, and this is equivalent to in all path globally not of phi holds. So, what it says that E f phi. So, there is a part where in future phi is true and negation says that this is false basically. And A g not of phi, it says that in all part globally phi is not true, and we are going to say that these two are equivalent. Of course, indeed you can get the internal feeling or intuitively you can say that yes, it is true, because in there does not exist any part where phi is true, and it is happened that in all part globally not of phi must be true. Again, just come back to look into some model, because we are going to have define the meaning of this CTL formula of a model. So, you just see that we are going to say that there exists a part in future phi is true and the negation of this one is true in this particular state S, and A g globally not of phi. So, in all part globally not of phi. So, if I am going to say that not of phi is true, not of phi is true, not of phi is true in those particular state. Okay. That means, in this part not of phi is true, in this part not of phi is true. But if I am going to say that phi is true over here, then what will happen? We are going to get there exists a part in future phi is true in this particular case. That means, not of there exists a part in future phi is not true along this path. To have this particular formula true over here, we should have not of phi over here. Then only we will say that in this particular part also we are not getting any state where in future phi is true. So, in this particular state S, I can say that not of E f phi is true, because there does not exist any state where in future phi is true. Okay. So, this is by looking into this particular model, we have found that again in S model show A g not of phi, because not of phi is true in all the states. So, if you consider these two formulas and you take any state of any model, you construct any model, you look for any state, if one is true in a particular state of that model, you will find that the other one is also true in that particular model. So, that is why you will say that these two are equivalent. Okay. So, again you will say that they are having the relationship between the existential quantifier along path and it is universal quantifiers along across the paths, and this is your existential quantifier of states and universal quantifier of states along a path. So, they are having a relationship. Now, another one, it is related to your next state operator. So, what is the next equivalent formula? We are getting that not of A x phi is equivalent to E x not of phi. So, first formula says that in all paths next state satisfies phi is false. That means, in all paths that phi is not true in next state. So, that means, second formula says that there exists a path, say in next state not of phi is true. That means, phi is not true, and we will find that these two are equivalent. Again, just look into a particular model. Say, if I am having a model something like that. So, in this particular state, so in all path next state phi is true, and indeed this is not true in this particular state S 0, then I can say that phi is true in these two states, but phi is not true over here. So, in all path in next state phi is not true, and this is equivalent to, you can say that we are going to get there exists a path in next state not of phi is true. Again, now if you are going to look any model and look for any states of any model, you will find that if one is true in a particular state, then other will also be true in this particular state. So, that is why we are going to say that these are equivalent formula. Now, what we have seen now, that we are getting that path quantifier A and E, and your that state quantifier, we can say that state of temporal operator, this is basically globally and your in future. So, these two can be treated as your universal quantifier, and these are basically existential quantifier. And by looking into these formulas, we will find that one is the dual operator. So, if A and G are there, they can be replaced by E and F, but in next state it is dual of itself, because next state is going to replace by next state operator only, but A becomes E when we are going to take the negation of this particular formula. So, that is these are the equivalent formulas that we are getting in your CTL formulas. So, in nutshell, we can summarize it like that. This is one equivalent that we have got, not of A f phi is equivalent to E g not of phi. So, if you take the negation of these two formulas, then we will find that A f phi will be equivalent to not of E g not of phi. That means, the formula A f can be replaced or expressed by E g. Similarly, second one that we have already seen, not of E f phi will be equivalent to A g not of phi. So, if you take the negation in both sides, we will say that E f phi will be equivalent to not of A g not of phi. And third one, which is related to your next operator. So, not of A x phi will be equivalent to E x not of phi. So, in that case, if you take the negation in both the sides, we will say that A x phi will be equivalent to not of E x not of phi. So, basically you see that A and F can be replaced by E and G, or E and F can be replaced by A and G. So, E will be replaced by A and F will be replaced by G. So, this is the things that we have seen till now. So, these are basically we are going to talk about the operator globally, future and next state. We are having another temporal operator, which is your until. Okay. Now, we will see whether some of this particular operator can be expressed with the help of until operator or not. Until is your binary operator, which involves two CTL formulas, and others F, G and X are unary operators. Now, you just see that we are having two equivalent with respect to your until operator. One, we are going to say that A f phi is equivalent to A t until phi, or E f phi will be equivalent to E t until phi. Here the symbol t that I have replaced it, basically it is the top, it says that the root value true. Now, when you see that when we have defined the semantics of your CTL formula, what we have seen that all state will be marked by this truth symbol true, and none of the state will be labeled by truth symbol false. So, what does it mean? That means true is true everywhere. This is the notion that we have while defining our semantics. So, if we take any model, say these are the model we are having, or say computational tree we have. Now, if we look into this particular model, that means true is true everywhere. That means all the states will be modeled by this particular truth symbol 2. So, that means it will be labeled by these things. We will say that true is true in all state. Now, what is the future operator f phi? It says that in a part we should get some states in future where phi is true. So, that means if you consider this particular part, that phi, if phi is true over here, then we will say that f phi is true in this particular part. So, similarly, if it is true in all those particular part, then we will say that f phi is true in this particular state S. And what is the until operator? If you say that phi 1 until phi 2, it says that phi 1 should remains true until phi 2 becomes true. Okay. So, in this particular case, now I replace this phi 1 by say t top or the truth symbol 2 true and until phi 2. So, now I am going to have this thing, that means true is true everywhere. So, true until phi 2. So, this is nothing but we are going to look for some state in future where phi 2 is true. So, this is basically nothing but we can say that f phi 2. So, that is why we are saying that the future operator can be replaced with the help of your until operator. So, A f phi will be equivalent to A true until phi, and E f phi will be equivalent to E true until phi. So, it is there exists a path in future phi is true, we will say that there exists a path true remains true until phi becomes true. Okay. So, we will consider these two as our equivalent formula, and similarly A f phi will be equivalent to A true until phi. Okay. So, now you just say that the temporal operator f can be expressed with the help of temporal operator until. So, these are another two equivalent formula that we have. So, already we have seen the equivalent formula which are related to A f, E g and A x, E x, and now we are getting two equivalent formula which are related to until and future operator. Now, if you look into CTL, computational tree logic, we are having 4 temporal operators, just we have discussed 4 temporal operator, and all those temporal operator will be preceded by path quantifier either A or E. So, in this case we will see that we are having altogether 8 different combination. Now, we need method for all those particular 8 different combinations or all 8 different CTL operator to check the truth values of a formula in a particular step. But since we have those particular equivalent, it may happen that we need not to look for the procedure for all 8 combinations or all 8 operators, CTL operators. We can come to a restricted set, and after that other operators will be expressed with the help of those particular restricted set. So, in that particular case, what we can say that AU, EU, EX form an adequate set of temporal operators for CTLs. Like your propositional logic or your classical logic, what I have said that disjunction, conjunction and negation forms a adequate set of operator, because with the help of these 3 operator we can express any other operator. Like that in your CTL also, now what we are going to say that AU in all part until operator, EU in all part until operator and EX, these 3 forms an adequate set of your CTL operators, because other operators can be expressed with the help of these 3 operators. Like that, say AX can be written with EX. So, if I am having EX, very well I can go for AX. Similarly, AG, EG, AF, EF can be written with the in terms of your either AU or EU. Okay. So, basically that is why you are saying that these 3 are sufficient enough to express all the 8 combinations that we have discussed till now. So, how this is a simple example that I am saying that I am going to take only EXP, AP until Q and EP until Q. So, this is the adequate set of operator EX, AU and EU. Now, since I am having total 8 combinations, so what I will have? I am having this another 5 combination operators. So, AXP will be nothing but that we have already seen the equivalent. So, you can say that this is not of EX, not of P. AGP will be equivalent to not of E, F, not of P. Okay. So, AX is replaced by EX, EGP is nothing but not of A, F, not of P. So, that G operators is replaced by F. Again, this F will be replaced by your until operator. Say AFP is your A true until P and EFP is equal to A E true until P. So, eventually all those particular 8 can be expressed with the help of these 3 operators. So, we can say that these are the adequate set of operators that we have, and with the help of these 3 operators we can express other operators also. But this is not the only adequate set of operators for CTL formula. We have some other adequate set also, but how we are going to get it? We can use just see that with the help of these things I need both A U and E U. So, in until operator I need both the combination E and A U. So, that is why we need these 2 things. Along with that we are having this particular either E x or A x we are going to take, but somehow if you can see that E u can be expressed in terms of A u or A u can be expressed in terms of E u, then what will happen? In that case I can just omit one of these 2 combinations. Then if we can omit one of these 2 combinations, then we are going to get some other adequate set of CTL operator. Okay. Now, whether is it possible or not, let us see. So, we are having one result. This is says that if this is until operator A until, this A until can be expressed with the help of your E until. This is E until. What it says that A phi 1 until phi 2. Say if we are going to look for this particular formula. So, we are having an equivalent of this particular formula. It says that negation of this whole formula. What is the negation of E? There exists a part not of phi 2 until this conjunct not of phi 1 and not of phi 2, or E is not of phi 2. Okay, till now we have discussed some of the equivalent formulas, and by looking into the construct of the equivalent formula, it is apparent that yes, they are indeed equivalent, and we can very well explain it also. But if you look into this particular equivalent, apparently it won't look that it is going to be equivalent, because it is having some complex combination. But indeed they are equivalent. We are not going to have a formal proof to see whether they are equivalent or not. For that we need some other information also, but intuitively I am going to establish the result, or with example I am going to show that these two are equivalent. Okay. Now, you just now look into the right hand side, that we are having these particular things over here. So, this right hand side, this expression can be written in some other way. So, what we are doing basically, it is nothing but we are simply using the De Morgan's theorem to this particular expression, that expression that I have in our right hand side. We know that De Morgan's theorem says negation of P or Q is equivalent to your not of P and not of Q. So, this is a De Morgan's rule. So, we are using this particular De Morgan's rule to this particular expression. So, what we am getting? I am just pushing this particular negation inside. So, I am getting not of E and this particular portion, and this or becomes n and negation of this second part. Okay. So, just using the De Morgan's theorem, and we are getting conjunct of two particular formulas. Now, what is this not of E g not of phi 2? So, already we have seen this particular equivalent, that A f phi is equivalent to not of E g phi 2. That means, we can say that we can replace this particular second part by A f phi, and first part will remain as it is. So, eventually we are getting this thing. Now, you just see that A phi 1 until phi 2, if I look into these particular things, A phi 1 until phi 2, that means, phi 1 should remains true until phi 2 becomes true in all part. On the other hand, what I can say that in all part, in some future state, phi should must true, phi 2 must hold, and along with that it should satisfy that all other preceding state phi 1 must hold. So, that is that we must get some future state in all part where phi 2 is true. This particular criteria or condition is captured by this particular part A f phi 2. Okay. And along with that, now we are saying that in all preceding state phi 1 must be true. So, this particular other second condition is captured by this particular part. Okay. Now, we will see these things. So, basically if we are having this particular expression, say this is the first part and this is the second part. So, f phi. So, we can now look for all possible part. Let us say that I am having, because this is A until. So, we may have many more execution part, since A phi 1 until phi 2. So, in all part this must be true. So, we will consider one particular part, and same thing must be true in all other part. So, it says that in all part in future phi must be whole, this second part basically. So, I will say that in future I am going to have this particular phi 2. That means, in this particular part in future I am going to get phi 2. And along with that, what it must say, that it must true this particular portion not of E, not of phi 2 until not of phi 1 and not of phi 2. So, what basically it says that I am going to get the formula E not of phi 2 until not of phi 1 and not of phi 2. Okay. So, we are having this particular formula and it says that it must not be true in this particular part, because I am having this particular negation. So, we are going to see this particular formula. What it says that phi 1 not of phi 1 and not of phi 2 true at some state, and till that point we should have not of phi 2. Okay. Now, you just see that I am getting this particular state, say considering this particular state where not of phi 1 and not of phi 2 is true. So, to become this particular formula true, then what will happen on all those particular state not of phi 2 must be true. Okay. And if in all those particular state not of phi 2 is true, then we will say that this particular part is true. Okay. And we should have the negation must be. So, this should not be true over here, that means it should satisfy this particular formula over here. Okay. Now, since your not of phi 2 is true over here, so it is not true at that particular point. So, till this particular point not of phi 2 will not remain true. So, negation is true over here. So, but what will happen in this particular step? Say if not of phi 2 is true over here. Okay. So, along with that, say if not of phi 1 is also true, then what will happen? Not of phi 1 and not of phi 2 will be true. So, in this particular case, what I am going to get? So, already I have said that in semantics, the fusion notion includes the present also. So, since this is both of these are true, that means eventually this formula will be true, but our objective the negation must be true. Since negation must be true, so eventually what will happen, that not of phi 1 must not be true over here. So, phi 1 must be true at that point, because we need the negation of this particular formula must be true. So, with this same logic, if we will find that if not of phi 2 is true over here, then we will find that phi 1 is true over here also, because we need this component must remain true. Okay. So, in this till this particular phi 2. So, in this way we will find that in all cases that phi 1 will be true. So, that means we are getting this particular part where phi 1 until phi 2 is true. And with this similar logic, we can extend it for all other part, and we will find that on all other part phi 1 will remain true until phi 2. So, what basically we have seen that a phi 1 until phi 2 can be expressed with the help of this particular formula. So, which basically involve E until operator. That means, E until can be expressed with the help of E until, or on the other hand we can say that E until can be expressed with the help of A until also. That means, we are having equivalence relation between A until and E until in all part until operators, and here exists a part until operator. So, now with this particular relations that we are having an equivalence between A until and E until. So, since we have this particular equivalent between these two operators, then what will happen? Now, we can get some other adequate set of operators. Now, what are these things? So, other adequate set of operators, temporal operators or initial operators, we are going to get different sets. So, first one already we have discussed, or already we have seen that AU, EU and EX. Okay. Now, what are the other things? You just see that if I am having until operator, if I know that AU is there, then it can be expressed as EU. Okay. Similarly, if I am having that next state operator, say this is your AX, then EX can be expressed with the help of AX. So, we need anyone from AU or EU, and we need anyone from AX and EX. And other two, so now out of that 4 temporal operator that we have discussed, that until and X already it can be expressed either A or E. Now, other two operators we are having F and G, infusor and globally. These are basically existential quantifier of states along a path and universal quantifier of states along a path. So, one can be expressed with the other. So, we can take any one of these two operators, because G can be expressed with F or F can be expressed with G. So, we will take any one of these. So, picking one operator from this set, picking another operator for until and picking another operator for that F and G, we can now construct or we can get several adequate set of operators. So, that is why we are just listing some of them, say these are treated as a adequate set of operators. So, taking one x E x, taking one u E u, and we are taking just one thing E g, because if I am going to take E g, then it will be expressed with your A f, and one we are having the A f, then we can express it with the help of your until or this thing. So, basically these are the similarly here also E g, then second I am taking A g, or I am taking that instead of A I am taking E u, E x and A f, or E u, E x and E g. Like that we can construct different adequate set of CTL operators. Okay. And we can see that we need at least 3 operators. With the help of 3 operators, we can express the other 5 also. Okay. So, we are going to get several adequate set of CTL operators. So, out of these particular things, I am going to consider say something and explain how we are going to see this. So, either I am going to take the adequate set of operators say E x p, I am taking that 1 x, I am going to take E u, E p until q, and the third operator either I am taking E g p. Okay, there exists a part in globally p holds or maybe A f p, because I know that E is dual of A, G is dual of P, either I can take this one or this. So, in this particular case you just see that if I know the procedure how to evaluate E x p, then I can very well evaluate A x p by looking into this particular equivalent. A x p is equivalent to naught of E x naught of p. We do not have any problem, it is very simple. Now, if A f p, then what will happen? You just see that I am having say E g p, then what I can say that A f p is nothing but naught of E g naught of p. So, if I know the procedure for E g p, then we can look for your distance A f p, or on the other hand if I am having this A f p, then I can evaluate E g p. Okay. So, that is why I am saying that either of this I can take. So, I am having this equivalent A f p is equivalent to naught of E g naught of p. Now, what will happen in A g p? A g p is nothing but we can say that naught of E f naught of p. That means, we are having this particular Fuchs operator. So, this is the Fuchs operator, and this Fuchs operator can be expressed with the help of A until p, A p until q is expressed with the help of this particular equivalent that we have discussed, negation of this whole formula E g naught of q or E until. Okay. And E f p, you just see that E true until p. So, we need this particular E f p for A g p. So, we are going to say that E true until p. So, if with the help of those particular equivalents, we can say that if I am going to consider only these 3 operators, then what will happen? Others can be expressed, and similarly, if I take E x p, E p until q and A f p, then others 3 can be expressed with the help of these 3 operators. So, we must know the procedure to evaluate at least 3 temporal CTL operators, then other can be expressed with the help of these 3. So, this is the power of equivalent formula, and we have seen that now we need restricted set, and we are going to work with a restricted set. So, this is the notion of equivalent in CTL formula. So, what is the notion? It is slightly different from your propositional calculus and predicate calculus, because here the meaning of CTL formula defines over a model, and that is why we will say the 2 formulas will be equivalent. To avoid that, in any state of any model, if the truth values of one formula is true, then the truth value of other formula must be true. Then only we are going to say that these 2 formulas will be equivalent. Okay. Now, this is the notion of equivalent. Like that, we can find some other equivalent also, but these are the basic equivalent formula. Now, we are having some other equivalent also, and we are saying that these are basically some sort of your recursive definition. So, what I am saying, just see those particular equivalent. We are saying that A g p is equivalent to P and A x A g p. So, A g p is equivalent to P and A x A g p. Similarly, E g p is equivalent to P and E x E g p. Okay. And A f p is equivalent to P or A x A f p, E p is equivalent to P or E x E f p, and like until A p until q is equivalent to Q or P and A x A p until q E P until Q is equivalent to Q, or P and E x E P until Q. Just see the nature of those particular equivalent. Actually, this is some sort of your recursive definition of those particular temporal operator. Here we are having 6 temporal operator. That means, these 6 temporal operator is expressed by themselves along with the temporal operator E x and A x, that next state operator. Okay. Just see that we know the meaning of E x and A x. If it is having a all part quantifier, then this A x will come into picture. If it is the quantifier is your existential quantifier E, then E x will come into picture. So, say A G P, I am having A x, E G P, I am having E x. So, all these operators, 6 operators are defined by themselves. So, this is some sort of your recursive definition of those particular temporal operators, and we are going to have those particular equivalent. Just see those particular meanings, how we are going to get it. Okay. So, first formula we are saying that A G P. Now, if I am going to have a model, just explaining with the help of model only, then it will be clear to you. So, what will happen? Say this is your S. I am going to say that whether in this particular model M, in state S, whether it happens A G P. Okay. So, that means, in all part globally P must be true. That means, we can say that I am going to say that this A G P will true in this particular state if P is true in all those steps. Now, I can break this A G P in like that. If I am going to look for this particular state, that means, in state M, in state S of M, it must model P. If P is true in S, then what will happen? We are going to see all the next states over here. Okay. What are the 2 next states of S? This is S 1 and S 2. In S 1 and S 2 now, what it should happen? Again in S 1 and S 2, A G P must be true. So, that is why we are saying that in all part in next state, A G P must be true. If A G P is true over here, then in both the states, that means, here I am going to get that in all part in next state A G P is true. Okay. So, that is why we are saying that if P is true over here, then I am going to look for those particular state whether A G P is true or not. Since I am going to look for all those states, that means, in this particular state I am going to say that whether in all part in next state A G P is true. So, that means, I am going to say that it will hold over here if again state S of model F, it models A x A G P. Okay. Now, you just see that if both these components are true over here P and A x A G P, then what we can say that this formula A G P is true at that particular point. So, I think it is clear to you that we are getting this particular thing. If both the components are true, then I can say that A G P is true over here. So, with the similar notion, we can go for E G P is equivalent to P and E x E G P. So, this is similar to your this one, but instead of looking for all part, it is your E G P. So, we are concerned about one particular part. So, what we are going to say? P must be true over here, and there exists a part in next step A G P must be true. So, E G P must be true. So, this is the things that for E G P, P and E x E G P. Okay. Now, similarly, we are having A F P is written as either P or A x A F P. Now, again just see that similar things that we are having. Okay. Now, what will happen in this particular case? I am saying that if P is true over here, then I am getting this particular part that F P is true over here. But already we have seen the semantics that in this particular notion of time, it says that future includes the present behavior also. That means, if P is true here itself, say I am concerned about this particular state. If P is true in state, that means, if S models P, then we can say that S model A F P also. Okay. So, if P models here, I am going to say that A F P models here. That means, this particular disjunct, it is a disjunct of two formula. If P is true over here, then I am going to say that A f p is true there itself. But if say p is not true over here, then what will happen? Then I am going to say that in all part in next state whether A f p holds or not. So, that is why I am saying that it is p or these things. If p holds there itself, then I will say that A f p is true over here. So, if p is not true, then I am going to look for this particular component in all part in next state whether f p holds or not. In all part in future, if whether in next state A f p holds or not. When A f p will hold, if I am going to get some future state where p is true. So, this is the way that we are going to say that A f is expressed with the help of A f only, but along with that particular A x operator. So, similar notion will go for E f p also. In this particular E f p, what will happen? Instead of A, we are going to have E. So, instead of looking for all parts, we are going to look for one particular part only. Okay. So, this is the way that we are expressing. So, this is another equivalent with respect to your future operator. Now, look for the other one, that until operator, A p until q. Again we are saying that A p until q is equivalent to q or p and A x A p until q. Again we just see that particular. So, again what happens, the notion of time, if you look into it, we have seen that when we are looking into the future behavior, we say that present scenario is also included in the future behavior. So, future includes the present. So, that is why we are going to look for A p until q, p remains true until q becomes true. So, this is having again two disjunct, okay, either first part or second part. Okay. So, if first part is true, that we will say that A p until q is true. That means, if q is true here itself, then we will say that A p until q is true, then we do not look for it. So, if q is not true at that particular point, say if not of q, then we are going to look for the second component A x A p until q and along with that and p. So, what does it means? That means, if it is q is true there itself, I will say that A p until q is true. But if it is not true, then we have to look for the second part, and what it must do, that p must be true over here, p and this is a p and A x in all next state, what it must hold? It must hold again A p until q, A p until q must be true over here. Okay. So, this is the way that we are going to look into it. Now, when I am going to look for that whether A p until q is true in this particular step, again I will look for these two conditions, either first check whether q is true there itself or not. If q is not true, then I will see whether p is true over here. If p is true, then I am going to see whether in next step A p until q is true or not. So, this is another equivalent, that A p until q is expressed with the help of A p until q, but along with your A x operator. So, similarly, we are going to get E p until q. In this particular case, instead of looking all possible parts, we will be concerned about any part. If these things happens in one particular part, we will say that E p until q is true in that particular step. Okay. Now, after going through this particular equivalence, now just look for some questions. Basically, we are going to check whether some of the some pairs of your CTL formulas are equivalent or not. So, the question I have given were like that, which of the following pairs of CTL formulas are equivalent? Okay. Here I am giving some pairs. So, first I am saying that EFP and EGP. Second one I am saying that EFP or EFQ and EF and P or Q. Third one is your EFP or AFQ and AF and P or Q. So, like that I am going to check whether those particular pairs are equivalent or not. So, first one you just see that I am saying that EFP and EGP. So, while I am going to check for equivalent, if they are going equivalent indeed, then what we will say that we will try to establish this logically. Okay. But if they are not equivalent, in that particular case what will happen? We will try to give a counter model. We will give a counter example, where I will say that in one particular state one is true, but other one is false, and in that particular case we will say that these two are not equivalent, because I am saying that what is the notion of equivalent? In any state, in any model, if one is true, then other must be true. Now, you see that I am having this particular formula EFP and EGP. Okay. So, EFP and EGP. So, in that particular case, I am going to consider one model. I will say that P is true over here. So, in this particular case, in this particular state S, I will get that S models E, F, P, and say all other state not of P is true. So, in this particular model, in S, I am getting EFP, the exists part in future P holds. Okay. But EGP, I am not getting any part where in all state not of P will be true. So, at least I am coming up with one example where in this particular state one formula is true, but the other one is false. So, in this case I am not going to say that these two are equivalent. So, these two formulas are not equivalent. Now, look for the second formula, we are talking about E, F, P or E, F, Q and E, F, P or Q. Now, in this particular case, what I am saying that there exists a part in future P holds or there exists a part in future Q holds. Okay. And whether this is equivalent to there exists a part in future P or Q holds or not. So, we know that if P is true, then what will happen always? P or Q is true, because either or, if P is true, then P or Q is always true. If P is false, then it depends on Q. Okay. So, if both are false, it is going to give me false. If any one is true, then it is going to give me true value. So, if P is true, I am going to say that P or Q is true. That means, if there exists a part in future, if P is true, necessarily I am going to get that there exists a part in future P or Q is true. Similarly, if there exists a part in future Q is true, then I am going to get a part where P or Q is true, because if Q is true, then P or Q is also true. But if there does not exist any part when P is false and Q is false, then P or Q is also false. You just see that if this particular part is true in any state, then this part is also true. If this is false, then this one is also false. So, in that particular case, what I can say that these two formulas are equivalent. Now, look into the third part. It is saying that AFP or AFQ and AFP or Q. So, this is also, if you look into these things, it is similar to your second formula, but instead of A, I am having E. So, this is the same property holds for your this particular OR operator. So, these two formulas is also equivalent. You can check it. Okay. You just try to check it. I am saying that this third formula is also equivalent, because this is the due to the property of this particular OR. If P is true, then P or Q is true. If Q is true, then P or Q is also true. Now, look for this particular fourth operator, fourth equation, AFP and AFQ and AFP and Q. So, we are going to say that AFP and AFQ. Now, AFP and this is the formula, I think I am looking into it, AFP and AFQ. AFQ and I am second formula I am thinking that AFP and Q. Now, you just see that I can look for any model, whether these two things are true or not, I am going to check. Just say that P is true over here, Q is true over here, say Q is true over here, P is true over here. Then what will happen? In all part, if I am going to look into these particular things, I am going to say that in all part in future P is true, because I am, if I go along this particular path, I am getting this particular state where P is true. If I go along this particular path, I am getting this particular true. And AFQ. If I go along this particular path, this Q is true over here, and if I go by the other path, then q is true. So, along all path A f q is true. But now, if you look into this particular formula A f p and q, then in along these two paths I am not getting any state where p and q is true, because in this particular state either p is true or q is true. So, A p and q is not true. Since A p and q is not true in any of the future states, so A f p and q is not true. That means, these two formulas that I have given over here are not equivalent. Okay. You understand these things. So, you have to see, because the notion of equivalence is in any state in any model, if the truth values of one formula is true, then other must be true. This is the notion of equivalent. Okay. Now, so we are saying that this is not equivalent, this is not equivalent, first one is equivalent, second and third one is equivalent. Now, similarly, again E f p and E f q and E f p and q. So, this is similar to the previous formula. Instead of your all path, now here I am having there exists a path. Now, in the previous example, previous model I have shown two different paths. Now, you consider any one of this particular path, you will find that E f p and E f q may be true in a state, but E f p and q will not be true. So, this formula is also not equivalent. Okay. Now, that next formula you see that A g p and q and A g p and A g q. Now, you try it yourself and see whether these two are equivalent or not. This is similar way, if you are going to say that these are equivalent, then logically you have to establish it. You can use any properties, the way I have used the property over here, that if p is true, then p or q must be true. If q is true, then p or q must be true. Like that, you look for some of those particular properties and try to establish if they are equivalent. And if you feel that they are not equivalent, then try to give a counter example. Try to come up with a model where you will show that one formula is true in that particular state, but the other formula is not true. So, if you are going to establish or going to show that these two formulas are not equivalent, then you should give me a counter example. Or if they are equivalent, then what you have to do? You should logically establish it. Then next formula, I am saying that T and A g p implies E g p and T and E g p implies A g p. What is this T? T is nothing but the top. I have already said this is the truth value true. Okay, just I will show one things. T and second formula I am saying that A g p implies E g p. That means, true is always true. I have to check whether this is a tautology or not. Okay. If this is a tautology, then the truth values will be always true, and in that particular case these two are equivalent. Now, what will happen? Intuitively I feel that this is tautology, because what I am saying that A g p. So, if I am going to say that, that means p is true over here in all state, then I can say that in this particular state A g p is true. Now, what is this particular implication? P implies q. If p is true, then q is true. That means, in all path globally p holds. That means, in state S, in all path globally p holds. So, in states I can say that it models all path globally p holds, because if I am just going to, for the sake of completion, I am going to give a self proof over here, and you will see that in all state p is true. So, I can say that in state A g p is true. Now, what is the second formula? Say there exists a path globally p holds. So, if p true, then second formula must be true. Now, here I am having several paths. Now, you can just think one particular path, maybe this particular path, because we know that if all path globally p is true, there exists a path where p is globally true. Okay, because we are going to get any path where this. So, if this part is true, then the second part is also true. So, this is going to give me the truth value true always. So, that is why I am going to say that T true and this particular formula, because this is some sort of a tautology we are going to get, because if this is true, this will be always true, and true is going to give me always true. Okay. So, that is why I am saying that this formula and this particular truth value true are equivalent. So, similarly, you can look for the other one also that I am going to talk about, T and EGP implies AGP. Okay, you just see whether they are equivalent or not. If they are not equivalent, then you can give a counter example. If they are equivalent, then logically try to establish it. Okay. With this, I will stop here today. Again, we will be meeting in our next class. Thank you.